Hi, hello. This is part 8 of chapter 3, and in this part, we are going to talk about atomic orbitals. In a previous part 7 of this chapter, we discussed about quantum numbers. Quantum numbers are the numbers that helps us identify the atomic orbitals where you can find set of electrons in the form of 2. Okay, so because we already know the three different quantum numbers and electron spin quantum number, the fourth, let's see, what is the word that I used previously? I couldn't remember. Uh, so because we already know three main quantum numbers and electron spin quantum number, we are going to use it to identify atomic orbitals where you can find electrons and discuss the characteristics of these individual atomic orbitals and discuss the shape of these atomic orbitals and work on a couple of problems on how to identify maybe quantum numbers from atomic orbitals, because you already know how to write quantum numbers, but what about coming back? If you already know atomic orbitals, can you identify the quantum numbers? So all of these problems we are going to discuss. Let's start our discussion with the basic s orbital, right? So the s orbitals, as you know, each shell has an s orbital. Shell 1 has an s orbital, shell 2 has an s, and shell 3 has an s because it starts with s. The angular quantum number L starts with s, 0, and for L is equal to 1, P, the shape. If L is 2, the shape is T. If L is 3, shape is 4. Four angular quantum numbers, four different shapes. So each shell will have an s orbital. So we already know what is the size of the shell is. Smaller, n is equal to 1, larger, n is 3, much larger, n is 4, like that, right? So what we are basically saying is, yes, there are s orbitals that have same shape, but if they were found to be in different shells, they are going to be in different sizes. And it is only true for s orbital because the shape of the s orbital is like no shape, because it just, everywhere. Like there is no x, y, z coordinates, because for s, the m value is 0, right? I'm sharing, just let me make sure I'm sharing, yes. So if you look at this number of the atomic orbital, principal quantum number is 2, so n is 2, and angular quantum number is L, but it has no XYZ designation underneath because s orbital has no coordination. It's kind of like all over 360 degrees angle around the nucleus. So that's why what we are saying is if shell is bigger, it should have larger size depending on which shell it is present. Let's look at this graphical image and discuss more about what I just said, that 1s is smaller than 2s, 2s is smaller than 3s. If you look here, you have the shapes of approximate shapes of 1s comparatively 1s to 2s. You know, this small cylindrical is 1s now. Compared to that, see how large is 2s. And in comparison to 1s and the 2s in the middle, and see how large is the 3s. And if it is difficult to see there, you can see it in these three. 1s next to nucleus, and you have no electrons, so kind of node there between shells. So another larger 2s electron cloud. And then here you have 1s, 2s, and no electron area, and a 3s. Excuse me. Excuse me. As the excuse me. As the size of the shell increases, the shape of the S also increases. And you can see it here in this radial distribution around the nucleus for the S orbital too. S orbital, like much stronger, let's say peak, which means strong interactions, but it's a smaller in shape compared to 2s, right? It occupies larger radius, smaller radius, larger radius. And compared to 1s and the 2s, look how large is the radius of 3s orbital. It is occupying much more radius around the nucleus. So all you need to know now is, yes, there are s orbitals, because s orbital is kind of like, circling around with no coordination, no small area. It increases in size as you go from 1s to 2s to 3s. And also the shape of the subshell determines the radial probability around the subshell of the nucleus. So what it means is, depending on what type of subshell you have, like S, P, or D, it will have a different preference to go as near as possible to the nucleus. Okay, so what does the s orbitals do is they shield, or the closest s orbitals of the nucleus try to shield the electron. So is every previous electron which try to shield the electron cloud. Excuse me, let me just repeat what I said. So the different subshells of S, P, D, F, they have a different, let's say, attraction towards the nucleus. So the shape of the s orbitals allows them to experience the maximum possible electrostatic interactions between nucleus and the outside electrons. So what you're seeing is, in comparison to subshell S is experiencing much more radial probability than subshell P, because the shape of the S subshell allows it to have much bigger electrostatic attraction with the nucleus positive charge. Okay, so it is because of the shape of them, and also smaller in size. It's kind of like, can sneak into it. So you can see that 2s is sneaking closer to the nucleus compared to 2p. And also it is explainable because 2s can only have 2 electrons maximum, whereas 2p will have 6 electrons. So 2 electrons can sneak in much more easily inside towards the nucleus compared to 2p. It cannot go much closer to shell 1. Shell 1 can only have 2 electrons, so it is impossible for it to go anywhere near. That's why you don't see much of 2p inside as much as 2s can go. Okay, I have one more example for you to digest what I'm trying to convince. And shell 3, discuss. Shell 3 has 3s, 3p, and 3d, 3 different subshells. According to what we discussed, the smaller the subshell, greater the chance it has to experience maximum radial probability. What it means is how much more exposure it gets with the nucleus. 3s, let's follow 3s. 3s has larger radial probability, see, larger radial probability compared to 3p, the green one, and compared to 3d, the lowest radial probability. So what it means is they are going to experience these electrostatic attractions from nucleus at a different capacity based on the number of electrons they have. So they are going to be distributed these electrostatic attractions differently. So the p orbital. The p orbital shape, we commonly refer to them as the dumbbell shape. And this is the general representation, like a dumbbell shape. Again, these shapes are derived from Schrodinger equation. The Schrodinger equations derive that the electron density of a subshell P looks like this in 3 different orientations. If you remember, the subshell P has 3 orientations of -1, 0, +1. So -1, 0, +1. And these 3 orientations are arranged in x-axis, y-axis, and the z-axis. That's why we call them as px, py, pz. And the d orbital shape, we can call it as, in general, double dumbbell shape. Most of them fits the description except this one. Double dumbbell, double dumbbell, double dumbbell, and double dumbbell. And d orbital has 5 different magnetic quantum numbers of -2, -1, 0, +1, and +2. And those are all arranged to have that number into these different orientations of x squared minus y squared, or z squared, xy, xz, and yz. And I don't require you to remember these orientations in this class. You just need to know that d orbital has 5 orbitals, and each orbital will hold 2 electrons maximum, and what are their quantum numbers are. L is 2 and ml is these many. Okay. And the general assumption for us is that, well, and it is true mostly, is each shell, subshells contain same levels of energy. The different shells contains different energies, but each shell contains same energy level subshells. Let me remind you how we come to this conclusion. If you guys remember, Bohr's equation, which is based on Rydberg's equation, helped us to identify the energy of an electron in a different shell. Like En is equal to -2.18 times 10 to the power of probably 31 multiplied with 1 over n squared, where n is the shell number, where we said if n is low number like 1, it will have low energy, so that we say ground state, and if it's n is 2, it will have a little bit more energy, and we say upper state, and if let's say if n is 4, it will have much more higher in energy. These are the energy levels that we talked about when we discussed about the En is equal to next to 2.18, those equation, energy of the electron. And if you remember, I used these words ground state and excited state, low energy state and high energy state. These are what I mean. Shell 1 is low energy state because these electrons has low energy. Shell 2 is higher energy state compared to shell 1 because those electrons have high amount of energy in them compared to all potential energy they were. And shell 3 has higher potential energy than shell 1 and shell 2. So we consider shell 3 in comparison to shell 1 and shell 2 as the excited states. That's how we use them. And what I'm saying here is, if you already have electrons in one particular shell, we assume that they all have similar amount of energy. Okay. And in future, again, in chapter 6 or 7, or maybe further down the road, I would say that, oh, S and P has different energies, but it's a different story. There are still minor differences between these two, but those differences between 2S and 2P is minute that you don't have to discuss them now. And you have to explain something based on the differences, these energies between 2S and 2P, then we discuss about it. That's why I included this additional information here so that you don't have to make up your mind in future. I'm just opening a possibility for you that you have an exception to this rule that we are saying, and we are trying to generalize. What we are trying to generalize here is correct. All the electrons in shell 1 in general have significantly lower energy than all the electrons in shell 2. All the electrons in shell 3 has significantly higher energy than shell 2. But within the subshells, there are minor differences that you don't have to discuss them now. That's why we're just saying that they all have same energy for now. So what here we are discussing is, just review of our atomic orbitals, how they were adjusted from ground state to higher state. So for shell 2, the primary quantum number is 2, so n is 2. So when shell 2 has a 2s orbital, which means the quantum numbers are n is 2 and l is 0. And when shell 2, when the atomic orbital is 2p, which means it has primary quantum number as 2 and angular quantum number as 1. And shell 3 has 3 different subshells of 3s, 3p, and 3d. Again, let me repeat, this is how you read it. Shell 3 has 3 different subshells, 3s, 3p, and 3d. Let's go into details. 3s means it has quantum number of n is equal to 3 and l is equal to 0. 3p means it has a quantum number of n is equal to 3, l is equal to 1. And 3D means it has quantum number of n is equal to 3, L is equal to 2. We're just not discussing the magnetic, but if you want, you can discuss that here, right, as well. All right. Let's work on a problem, see how we did in this topic. List the values of n, L, and ml for each of the orbitals in 4D subshell. Okay. It is asking you to list the quantum numbers of n, L, and ml for the 4D subshell. I'm assuming by this time you already know how to do it. So give a, pause the video, try to identify it. Anyway, I'm going to show you now. I hope that you got the right answer when you pause the video and try to identify yourself. What you try to do is you try to decode the number based on the directions that we use. We use a numerical integer for a primary quantum number, and we use English letters S, P, D, F for the angular quantum number L, and based on the angular quantum number, we define how many of the magnetic quantum numbers we get. So based on that, that is how we do. That's basically that explains that, right? So based on that, your n for 4D has to be 4, the primary quantum number. Your D has to be 2, because S is 0, P is 1, D is 2, F is 3. And for L is equal to 0, MLR minus L, 0 plus 1. So it has to be -2, -1, 0, +1, and +2. Okay. And you can always refer to this slide, what we just showed you earlier. For each shell, how many angular quantum numbers you will have, and how many magnetic quantum numbers you will have. Okay. And in addition to that, I also find this on internet that basically summarizes all 3 quantum numbers and their magnetic spin quantum number as well. This is for all atoms in the periodic table that you could refer to identify the quantum numbers for any particular element, what quantum numbers they will have, including the electron spin quantum number. Let's just randomly look at an element. Let's say you have, I want to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 2, 3, 4, 5, 6. Let's say you have carbon. So carbon has 1s and already 2s filled, and in 2p it has 2 electrons, and they have a spin of +1 and +1 because you are putting 2 electrons. All 3 electrons is going to have +1 first, and rest of the 3 electrons is going to have -1, -1, -1. And when we discuss the next topic, electronic configuration, you know why it is first 3 are +1 and next 3 are going to be negative halves. All right. That's all for this topic. I'll see you again in next part called electronic configuration. That's the summary of these quantum numbers and atomic orbitals is basically electronic configuration. And in chemistry, whenever we ask anything, whenever we try to identify chemical reactivity, we start with electronic configuration of an atom. So next topic is also pretty important.